This is really a first for me, to be in such a beautiful auditorium, so old and venerable. And so I thank you very much for this invitation. Thank you, Mr. Rector. Thank you, Mr. Vice Rector. Thank you also, Luis, my friend, Luis Rosso. And I have to say that this morning, I was touring this, the laser, the CLPU, and I was very, very impressed. And you should all be very proud to have in this corner of the Iberic Peninsula, this absolutely gorgeous laser, which I think is going to illuminate the science of this country. And I have to say that I have to thank again Luis, Professor Rosso, because it was certainly not easy to have done what he did, because he started from scratch and to build this from the ground up, to build this beautiful facility. But we are going to see many, many users, and which is really going to really make Europe, bigger. And so anyway, so this is what I want to say, because I think it's remarkable, and I hope that everybody is going to go and visit CLPU, not at the same time, okay? Okay, so now I'm going to discuss basically what has been the topics of my Nobel Prize. The reason why I got the prize, which is, of course, a very, very important moment in my life and your life. So I think the reason I got the prize is because I had always this passion, for lasers and light. And in fact, when I started my research, the laser was only a few years old. And I could see its evolutions, which has been really absolutely amazing. And I contributed already to increase its contribution by demonstrating this technology that we are using now. So here I just want also to illustrate that the fact I like this picture because it shows me Donna Strickland and during the Nobel celebration, and Donna was my my student 35 years ago, and when I got this phone call from Sweden, I was on my way. It was 12 o'clock. It was, of course, the first Tuesday of October. This is where they announced the Physics Prize, and and I was on my way to the swimming pool, and when I got this phone call, and the chairman of the Nobel Committee told me that I got the prize. So I was proud, of course. But he said, well, but also you are going to share it with your former student, Donna Strickland. And I was elated, of course, to hear this. And because not only I had the prize, which is, of course, is something very, very difficult to get, I have to say, and but also to have trained, the third woman to get a Nobel Prize. Donna Strickland was the third woman in 120 years to get the Nobel Prize. And so I was also very, very proud of this. So anyway, so I'm going to tell you now what we did with Donna to get the prize. Okay, first of all, okay, where do I, oh, sorry. Yeah, first of all, I have to tell you that just generally that the light was not always with us. Okay, first the light had to wait to have the Big Bang. Okay, Big Bang was started 14 billion years ago, but the light came only after 400,000 years ago, after the Big Bang, okay? Because the light had to find its way through this really soup of particles and so on. So it was not, so light came. And it was incoherent light, what we called, like this light bulb. This light bulb emits, this light bulb is coherent light, okay? Incoherent light, I'm sorry, incoherent light. And this is important. But after, in the early 60s, the laser was demonstrated, and we could now produce coherent light, okay? We can produce coherent light in a continuous way. This is what this laser is doing. Or we can produce coherent light in a pulsed regime, okay? And the duration of these pulses can be extremely short, in a femtosecond regime. And this is a type of pulse we are using. A femtosecond is a billionth of a millionth of a second, okay? And the light travels, it takes a second to go to the moon. During a femtosecond, the light travels really a small fraction of a red cell, okay? So just to illustrate my point, saying that how short is the light. Now, the pulses. Now, I talk about coherent light, incoherent light, and so on. Let me explain the difference between incoherent light and coherent light. And if I take this analogy as a marathon, for instance, and you see these marathons here, you have a bunch of people, maybe 10,000 or so, people, they're all dressed differently, they all run differently at different pace and so on. They don't know each other, okay? They are completely independent, okay? And they are going in a general same directions and trying to win, of course, the marathon. Now, you see, this is very chaotic as opposed to oh, what's going on? No. Yeah. So you see these marathons which composed of these people and running, they don't know each other and so on. Oh, yes. This, what's happened here? Come on. Damn computer. It doesn't work as well as lasers, Anyway, I cannot, I'm sorry, but I cannot really. I don't know if someone could really help me here. Just let's see, maybe you can move forward and yeah. Yeah, very good. Thank you very much. Now I have to be careful. Don't go too far. Don't go too far. I may need you. Okay. So this, you see, I'm contrasting these marathon runners, to really marching soldiers, marching army, And marching armies, they're all dressed the same. They all walk at the same pace. They don't know, they know, maybe they don't know, but they, at least if you know the position of one soldier, you know the position of everyone, Very, very methodical, very rigorous. And so this is what is coherent light as opposed to incoherent light. Okay, so now the first person who has demonstrated a coherent light is this gentleman, which name is Ted Nieman. Okay, and Ted Nieman produced for the first time, almost exactly 60 years ago, 59 years ago, demonstrated the production of coherent light. And what is amazing, and this is what is the point of my talk here, is the fact that with this coherent light, you can really do things which are incredibly different. First of all, you can take this light, this incoherent light, to slow down atoms, okay? And to a very, very small velocity, almost they are going to become immobile, okay? And this is what we call the field of cold atoms. We are cooling atoms, and I understand in 2012 you had Cohen Tanuji, who had also a Nobel Prize for this kind of things, where they were able to slow down atoms. Okay. Now, okay. So this is slowing down atoms. This is really I'm going to find a way to okay. So and so you see that you can use this light to slow down atoms, but also now you can use this light to increase the velocity, to accelerate particles, and this is exactly what we are doing and what is being done, by Professor Rosso in his laboratory. We can really now accelerate particles, to the speed, the light velocity. And these particles can reach energy of the giga electron volt, and hopefully soon in a regime of tera electron volt. So you see, here you have two applications with 1 electron volt light. This is the way we like to express it in electron volt, the energy. And so you can really go to 10, you can slow down atoms to very, very slow speed and to very high speed. And in fact, it goes from 12 order of magnitude in every way, in each way. And which means that now with light, with only this light, you can really go into 25 order of magnitude applications. This is phenomenal. Okay. Now, how can we do that? Now, can we accelerate particle and so on with very, very, with light? Well, we make it very intense, very, very powerful. And in order to get it very powerful, what we do, we are going to produce a burst of light in a very short time, okay? And for instance, we will be able already to produce a petawatt power, okay, with lasers. Petawatt is 1,000 times, okay, the power of the global grid power, okay? That's going to be a petawatt, you know. This is remarkable, right? But we do it because we are producing a relatively small amount of energy, you know, in joules over femtoseconds. Okay, femtosecond is so short, but because the power is energy divided by time, you can produce this type of power. Okay, because the time is very, very short, and this is the trick. So you see, we can produce for femtosecond, we can produce this type of light. Now, if we can now take this power, focus it over a micrometers, which is a 50th fraction, very small fraction of your size, then we can reach incredibly high pressures. The pressure that you will feel if you were capable of having 10 million Eiffel Tower on your finger, okay? And so this is something which is, of course, very impressive. So it's yeah, so we are, by using, this is really nice, I think. So by using these lasers, and the size of the lasers is not very large. You know, here I show you a laser. I showed you a laser, which was really the size of this a small fraction of the room, but we can really produce, you know, as I say, 1,000 times the big power of. What's this? Why doesn't? Could you stay here around? Yeah, and click it for me because I cannot really. Yeah. I'll go back first. No. Can you? No, you have to do that. Yeah. You go if you want to go back. Yeah. No. Yeah. This is one click. One more click. Yeah. Okay.
This one? You want?
Yeah, no, the previous one.
Previous? Here.
Okay, this is the tab. Okay, stay here.
Okay.
You have a nice, you're feeling comfortable?
Yes.
Yeah, great. Okay, good. Okay, so I will tell you when to click, okay? So this is typical laser, and if you go to see Professor Rosso laboratory, you would see it. It's not very large, but it's capable of producing 1,000 times the power of the world grid power, but of course in few femtoseconds. So now click. Yes. So this is really this is being done because of this invention that we did with Donald Strickland, where we showed how we could produce this power, and so because it's a phenomenal power, okay. So you have to be very careful. And so what we do is we start with a very short pulse, you know, in femtosecond, you know, and then, but we don't try to amplify it immediately, because if you were amplifying this pulse immediately in this amplifier, you know, which is this amplifying material, you will blow these amplifiers, okay? Because it's power is so important. So instead of doing that, we are stretching the pulse by 1,000 times. So we decrease the energy, the power by 1,000 times. So now we can really extract the energy 1,000 times better. And then once we have extracted the energy, we use the same device, basically, really to put the pulse back together. So now you have the energy which is extracted by the amplifier and which is put in a very short time. Okay, so we circumvented, the problem of amplification this way. This technique is called CPA, chirp pulse amplification. Next slide. Yeah, and what is very, very important here, and that's the reason why this field is important, is because with extreme light, I call that extreme light, we are capable of producing the largest peak power, the largest temperature, the largest pressure, the largest acceleration, the largest field. So from this laser, it is really a universal source where you can do so many things. Next slide. Next slide now. Also, next slide. Yeah. So now, also, what is very important about these lasers, okay? Because it revolutionized laser physics, really. Before this laser, we had lasers was limited to what we call atomic physics, okay? The science of physics which deal with atoms, okay? Atoms, remember, it's a nucleus here, a nucleus which is surrounded by the electrons, which moving around, okay? So atomic physics, basically, you study the motion of these electrons, okay? Now, because we are able to accelerate this particle to the speed of light, produce particles in very, very high energy, now we can address the nucleus here, which is very, very important. We couldn't do that before, and so we could now go from atomic physics to subatomic physics, which means nuclear physics, high energy particle physics, and so on. Okay, next slide. So now this is really the progress, in power that we have accomplished since the 1960, when the laser was discovered. Okay, where you had a very rapid increase in intensity at the beginning, and then a plateau. And the plateau comes from the fact that you couldn't accelerate, you couldn't amplify the pulses anymore very quickly. So you had a plateau for about 20 years, and then we came up with this idea with Dana of chirp pulse amplifications, and which really made possible now really to climb, really to increase the intensity by another 6 orders of magnitude, a million times. And now we are contemplating also to go much higher. We are going to do that with, of course, the type of lasers which are existing at Salamanca now. Okay, next slide. Okay, there is this, with Salamanca, we have also this extreme light infrastructure which was built by Europe, where you have also three very large lasers. And what we are trying to accomplish, in Europe, is that all these lasers be coordinated, and we are talking to each other and so on, and they are very, very successful because they are very, compared to the number of users, the number of lasers is very relatively small. So, this is very good for the facilities because they have many users. Okay, next slide. Okay, now very quickly, this is, as I said, we have this curve, and with different intensities. And of course, at every every level of intensity, you have new applications. I'm going to first to describe eye surgery, and this eye surgery and micromachining that we can do in a relative low intensity. This is for us, it's relatively low intensity, and but you can do really very nice machining, and you will see also surgery, eye surgery, and so on. And so the next slide. Yes, this you see, if you use a long pulse, and you want, say, to machine something. Okay, so you have a target here. You would like to ablate some material, and you see you cannot do that in a very clean manner because the pulse is long. Here, the pulse is long. For us, long means nanosecond. I'm sorry, but already this is very short for most of you. But for us, it's very long. And so if you are using this type of pulse, for machining, you have some collateral damage because you are putting the energy in a very small area, and the heat, propagates and then make a big crater here. Okay. Now, if you are using, of course, a very short pulse, no. If you are using a very short pulse, then you see you do the same, you deposit the energy, but this time the heat doesn't have the time to propagate because it is so fast. Okay, next slide. So that you see you have no collateral damage, and you can see that are some of the example where we micromachines, some material. It can be almost virtually anything, because anything can withstand the type of intensity we can produce with CPA laser. So, but anyway, you have to adjust it, of course, but here you have an example of micromachining that you can do. These holes, for instance, are a fraction of a micrometers in size, okay? And you see how sharp are the edges, okay? The edge here is very, very sharp, okay? So you have no collateral damage, okay? Very small amount, at least. So next slide. And one, of course, one nice applications of this fact that we can really macro machine things without any collateral damage is, of course, the eyes. Okay, and now you will see that you can really, for different procedures, if you have myopia or hypertropia and so on, if you have a problem with cataracts and so on, very likely that you are going to use the femtosecond laser. I'm going to show you why. Next slide. So, for example, this is working on cataract, not on cataract, but cornea. This is really to improve the visions. You have to change the flatness of your cornea, okay? And by creating some, structures or creating flap, just to speak simply, of the cornea. And so you focus the beam in the cornea, okay? So you are going to ablate a very small amount, small volumes, okay? Very, very precisely. And then you are going to move the beam around, so you are going to create a flap, okay? Now, if you are, next slide. If you are, for instance, using long pulses, like for us again, it's long, 50 picoseconds, 10 minus 12 seconds, but for us, it's once again, this is relatively long. And you see, in this we did some experiment on a pig's eyes, okay? And you see that you are making a mess, okay? The cut is not good. But on the other hand, if you are using femtosecond lasers, you can do your flap cutting and so on very, very nicely. These are kind of also, we do it now very, very well. What's amazing, you have about 24 million eyes operations since the beginning in 2001, okay, when we launched this, the first product. And now, it's amazing. It's very, very successful application. Okay, applications now. And the other type of things you can do with the eyes, you can, for instance, do grafting, okay? And for instance, if part of your cornea is bad, what you want to replace it with good cornea from a donor, who is usually dead, okay? And so you are going to cut it with a Trifine, you are going to cut it, remove this piece, and you are going to replace it, by another one. This is what we do normally, but now we can do that by we can shape the cornea here and here, so we can really put, the implant, we can push it in, and you have more surface area, so it's much better, for corneal surgery. And here again, also, if you have a top part of your cornea, which is bad, we can just replace the one top which is bad. Now, next slide. Now, we are going to go up now in intensity, and we are going to go in this green area. So this green area is very, very important. This green area, there is something magic which is coming, is the fact that now the light will accelerate particles, okay? It will accelerate particles because there's few reasons, but anyway, now the field becomes so large that the electrons, if the propagation axis is this way, the electrons are moving this way in regular optics, this way. But now when you are in a regime where you are in a relativistic regime, the electron now move relativistically, which means that its mass is changing, and it moves up and down, and because the action of the magnetic field and electric field result in a propagation which is parallel to propagation direction, and then you are accelerating the particles. You can do the same thing after when you are in an ultra-relativistic regime, not only with the electrons, but with the ions. And here, in the yellow area, this is, is a regime where we break down the vacuum, okay? You break down the vacuum in particle and anti-particle, okay? And this is what we would like to go, okay? So we will basically materialize light and vacuum. Okay, next slide. So let's start with now going to the green area that I described and show that we can really accelerate particles very efficiently. And we are using a concept which was put together, which was really put together by Toshitajima and Dawson in '79, and where they had the idea to first with the light to create a plasma wave, and the plasma again is a kind of a soup of electrons and protons, and you are going to produce a wave, and this wave is going to accelerate not a surfer but the electrons. And it's a very, very efficient way to accelerate particles. Okay, so next slide. Yeah, so the way we do it, and if you go to CLPU, you will see, you take a laser, high intensity lasers, and then you focus the laser into this jet, a supersonic jet. And what you are going to do, you are of course going to, you are going really to break down the atoms which compose this jet and create a big plasma wave. Okay, and this plasma wave, you are going to use the electrons are going to fall in the trough of the wave and be accelerated, you know, as they are doing that by this laser pulse to the speed of light. Okay, and already this is working extremely well. Extremely well. I mean, this concept is phenomenal, and we can accelerate particles to what we call giga electron volt per centimeters. Giga electron volt per centimeter. This is phenomenal, because if you had to do that now in a conventional way, next slide, then this is a type of machines you need, okay, to do that. That's a synchrotrons. And this synchrotron machine is producing 3 GeV, okay? And we can do that over centimeters, okay? So you imagine reductions of the technology. You know, we go to large scale facility to really now a tabletop facility, okay? And which means also you can multiply the number of these machines, because they are, of course, much less costly. Okay, now next slide. Yeah, this also, just to give you an idea of what we can do with laser accelerations. This is a ring which is laser particle acceleration at CERN. Okay, CERN, they want to accelerate particles to TeV. Okay, tera electron volt, and it takes the accelerator has to be about 27 kilometers. Okay, to do that, which is of course, you know, very large and very costly, because you have to make a 27 kilometers, you know, tunnel, and full of instrumentations, and so very, very costly. Now, if you are using lasers, next slide. Yeah, so that is microwave technology. Okay, that's traditional technology. Now, next slide. Sorry, yeah, next click. Okay, if you are using laser wave field acceleration, you are talking not about kilometers now, but you are talking about hundreds meters. Okay, so and next slide. Yeah. Okay. So could you come back? Just want to see. Yeah. So so you see that these phenomenal reductions. And right now we are really working on concept with what we call laser wave field, not in gas, but in a visible, where this time the accelerator, this type of accelerator could be on the tip of your finger, okay, on the centimeter size. And so what is important, of course, if I do that, I can go now to much, much higher. Not only I can reduce the cost of this type of instrument, but we can go much, much higher in energy, like beta electron volt, PeV, which is 3 orders of magnitude 1 TeV, and which is now only the cosmos can produce this. What's going on in the cosmos, you can produce fast. Okay, next slide. Okay, next slide again. Yeah. So now another applications is the accelerations of ions or protons. Next slide. Yeah. What is very, very important is many applications, needs protons or neutrons. And so you want to produce these proton neutrons if it's possible. Now we can do it very easily, relatively easily with laser wave field with CPA system, very easily to the MEV regime. But you'd like to go to PEV regime for many applications. So, but when we want to produce a very MEV protons, it's very simple. Okay, take a very thin specimen of it can be plastic or it can be metal, and then you shoot the laser, and then what happens is you are pushing the electrons because specimen is made, of course, of electrons and protons. You push the electrons, and the ions protons are going to follow. This is one of the mechanisms. Okay, so the electrons move forward, dragging the proton behind, and so you should be able to get very, very high energy, especially if the laser is very, very, very short, like a few femtoseconds, but that's another story. Okay, next slide. So next slide again, yeah. So you see this, if you really want to produce hundreds of MEV protons, this is a type of machinery you need, okay? This is 600 meters, okay, full of instruments and devices and so on. Plus it's cryogenic and so, very, 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 very expensive, okay? And when you think that you can do that with really high intensity lasers with a piece of plastic, this is really incredible. So that I will say that this is really will increase and will make possible many, many applications where you need high energy protons. Okay, and I'm going. So next application, and among the applications you have of protons, you have nuclear medicine and proton therapy. Okay, proton therapy is very nice because let's suppose that you have a patient with a tumor, for instance, in his brain. You have ready to, you can shine the proton beam at this time, proton beams on the tumors. But what's nice is the fact that you can burn the tumors without affecting all the healthy tissue which sits before the tumors, okay? And so, of course, this is very, very, of course, very, very important. And so that's one of the big, big applications of protons. Now, what you can do with protons, of course, you can also produce isotopes, and isotopes, are you can use some of the isotopes, which are radionuclide, and implant them, in a tumor of a patient, so to cure the tumors, the patient. And then you have nuclear diagnostics also, very important, where you are producing this radioisotope that you are using for like PET scan, for instance, and so you need them, okay? So they can be produced, they could be produced now in a laboratory, okay? Now they have to be produced elsewhere, where it takes time, for the drug, the radioisotope to reach the patient. You like to have, maybe to produce them near the bed of a patient. Okay, next slide. And the other one, which is very, very important in my mind, is it's really on the top of my agenda right now, is really trying to, with CPA, with short pulse amplifications, trying to do something about nuclear waste. Because we know that nuclear energy is certainly maybe the ideal energy, because you don't produce CO2. But of course, you have a problem because you have to deal with all this nuclear waste, which are going to be emitting, for bad radiations for sometimes millions of years. So one way to mitigate this problem, is doing transmutations. And transmutation is a very attractive, very elegant and attractive concept. If you can produce neutrons, high energy neutrons, and this is something you can do with a CPA system, CPA laser, is you can irradiate the nuclear waste. The nuclear waste is made of there are 4 bad elements which are bad. I mean, you have neptunium, you have americium, you have curium, and plutonium, which are really bad. Okay, so you want really to transmute them. That is, you want really to change the nucleus of your atoms by bombarding this nucleus with high energy neutrons. So if the neutrons are energetic enough, you can fission this nucleus. Okay, you can fission it, and so you end up with byproducts, for instance, which is composed of 2 nuclei. Okay, but this nuclei now, emits only, in this case, for instance, during 11 minutes, or 21 hours, which is of course far less than 2 million years. Okay, so this is a very attractive idea, and the fact that people, some reporter this morning say, well, we haven't done that before. Well, the reason we haven't done before is because we don't have the accelerators are not small enough and not cheap enough to make this procedure, economically viable. So this is what certainly what I like to push, because of course energy is very, very important for our society. It is a top commodity, to do. So this is, of course, very, very important. So you have seen application in the medical application here in for environment. Now let's also go back. Okay. Now another important applications of CPA is the space debris. You know that since 1957, when the first Sputnik was launched, okay, we have launched enormous amount of, very large amount of satellites, which correspond. Okay, this is the amount of stuff that we send in space. We send in space the equivalent of 28,000 tons, or about the equivalent of 4 Eiffel Tower. Okay, and 1 Eiffel Tower is under the form of debris. Okay, orbital debris, which are circumventing the Earth at 15 kilometers per second. 15 kilometers per second is 10 times the speed of bullet, the fastest bullet. Okay, 10 times. So the space is going to be a battlefield, okay? So we would like to do something about that. And as we said, we are developing for the application I mentioned before, lasers which are at very high repetition rate, okay, like thousands seconds or something like that, and also they can be used really maybe to remove the debris. Okay. Now the way we would like to remove the debris is, okay. Could you next slide? Yeah. So we have a laser here, and when we see a laser, when we see a debris, okay, we shoot at it, and the next slide. Next slide. Yeah. And we have this, this debris here, and we shoot the lasers, and what we are going to do we are not going to really blow up the bolt here, but we are going to just ablate a small section of it, which is far less expensive in energy, okay? And this, when we ablate a fraction of this bolt here, you have a rocket effect. And this rocket effect will have the consequence of moving the debris, change the debris in orbit, and so this debris will be absorbed by the atmosphere, will be burned when it's going to enter the atmosphere. Now, of course, you say, of course, there's not only you have small debris, you have big debris. The big debris, which are which are very big, like as I say, like a washing machine, maybe. And of course, you cannot really use this technique because, first of all, you can really detect them from the ground, and then what you can do is, if you see one of these big debris coming to close to or on the path on the trajectory of the satellite you would like to protect, then you move the satellite. That's the way it's being done right now. But of course, the big problem also are the small debris, because they are so numerous. You have millions of debris like this now. Okay, and that's going to accelerate, because now we launch debris by thousands at a time. Okay, so you can imagine what's going to be the space is going to be in year to come. So right now it's okay, but I think we need to develop some technology, to clean up the space. Okay. Now what is next? I'd like to conclude here by saying that now this extreme light, and I'm really proud to be here, to have seen the system this morning, beautiful system. But so extreme light is capable of generating the largest field, the largest acceleration, the largest temperatures, and the largest pressures. And in the spirit of Nobel, because this is what Nobel wants, he wants his prize to really encourage, to benefit humankind, okay? And so I think this extreme light now carries the best hope and our opportunities for the future of science and technology and society. Now, before I stop, I'm going to go to the next slide. Oh, and the best, by the way, and the best is yet to come. But next slide. I have to talk about the Nobel Prize a little bit. Okay, so of course the Nobel Prize is something which is absolutely very, very imposing. Okay, it's very impressive. It's very well done. I mean, you are really proud to be on the stage. This is myself receiving the prize by the King of Sweden, and this ceremony is followed by a very nice also ceremony. Go ahead. Yeah. You know, where you have about 1,200 people, and for instance, here I'm sitting next to the Queen. Okay, Donna Strickland was sitting next to the King because you know physics is first in the Nobel Prize. Okay, and she was a woman, so she was sitting next to the King. Here I'm chatting with the Queen, and next slide. I was next to the Queen, and also I was next to the Princess Sophia. So we had a fabulous time. Really, it's very, very impressive, very, very glamorous. Okay, but I have to say that about this all the Nobel Prize events, you know, ceremony and all that. The one I really preferred is this one. Next slide. This one, yeah. This one shows the last thing you do when you get the Nobel Prize. Last thing you do, okay, is to, I mean, the clerk, which is here, brings you in this really in this room, you know, a small room, you know, nothing special, okay. They bring you this notebook. It looks like a notebook, not really, also not something very impressive, you know, just notebook. Except that in this notebook, you have all the signatures of all the Nobel laureates. So you have everybody in this notebook, and it's very emotional to read it. You know, you have a signature of Einstein, you know, Planck, and you know Steinbeck, and you know everybody. Okay, so very, very, very impressive. And here, you know, it was very emotional for in fact for me, but also my wife Marcel, which is next to me, you know, to have reached this point, you know, where you sign, you know, this book with all the Nobel Prize, and I was very, very pleased to have Marcel, of course, with me. She has been with me for 52 years. You know, we have been married for 52 years, and so it was a very emotional moment. And I just want, with that, I would like to thank you very much. Thank you.